All right. Okay. Okay. Yeah. Let's check the audio. 1, 2, 3. Let's play this. 1,
If
2,
you have
3.
polarized sunglasses, you have a quantum measurement device.
Each of these pieces of glass is what's called a polarizing filter, which means when a photon of light reaches the glass, it either passes through or it doesn't. And whether or not it passes through is effectively a measurement of whether or not that photon is polarized in a given direction.
Try this. Find yourself several sets of polarized sunglasses or old photographic filters.
One, two, three. 1, 2, 3. Is it live? 1, 2, 3. Okay. Everything is fine. Everything is fine. Okay, we'll come back to this.
Down or different. We'll repeat this.
One early morning, away from the distractions of all your devices, an Arvin Ash moment hits you.
This episode is supported by 23andMe. Hey, I'm Diana, and you're watching Physics Girl. I want to talk to you about whether the laws of physics are possibly wrong. Like, so wrong that, say you made a quantum computer to encrypt your $1 million self-driving AI butler, but because we got the laws of physics wrong, it could be hacked like that. Chances are the laws are not wrong, because we've tested this stuff a lot. But it's kind of the point of science to be skeptical. Sometimes you have to revise laws. Like when quantum mechanics was first discovered, classical mechanics couldn't fully explain light. To this day, physicists are testing accepted laws of physics, and this video is about a brand new experiment with breaking results, testing quantum behaviors using lasers and telescopes and stars 600 light years away and the Austrian National Bank.
My name is David Kaiser. I teach physics and the history of science here at MIT.
Dave Kaiser and his colleagues have conducted an experiment to test whether quantum entanglement is real. But first, we've got to get on the same page about quantum mechanics. Quantum mechanics is a physical theory that describes how the tiniest things in the universe act, and some of their behaviors are weird.
You know, we've had quantum mechanics in one form or another now for 90 years, not quite a century of quantum mechanics. It has never failed us. It has led us to predictions, albeit probabilistic ones in most instances, that match observations sometimes to extraordinary accuracy. Sometimes we can match to 13 decimal points. That's amazing. And that's by far the most accurate scientific theory ever developed by people and tested. But it also has these very strange sort of
I keep hearing this, but I don't know what they're talking about. What is this accuracy? What are we talking about?
inbuilt features that still make some people uncomfortable.
In other words, Dave agrees. Quantum mechanics is strange stuff, like quantum entanglement and Schrodinger's cat. Schrodinger's cat was a thought experiment devised by Erwin Schrödinger when he thought that quantum mechanics had become just too strange. The math of quantum implies something called superposition, where a quantum particle can be in two or more states at the same time when you're not observing it. Take, for example, spin, which is a property of particles. If you don't know what it is, you're probably...
Yeah, they always talk about spin. So why don't we talk about something else besides spin? It's always spin. So maybe we don't understand spin. You never talk about the mass of an electron. You never talk about anything else. It's always the spin. Take, for example, the spin. Yeah, let's skip that. Let's go to a different example. Oh, you don't have a different example. Oh. So why did you say take for example? That's weird. Why is it always spin? Let me see. Quantum entanglement. Let's go to ChatGPT. Oh, you know what? Let's use this first. Quantum entanglement that is not spin. Based on that, quantum entanglement is typically associated with spin correlation chain. However, there are other aspects of entanglement beyond spin. Here's the position momentum. In some systems, such as ultra-cold atoms, energy time entanglement. In quantum systems with finite lifetimes, energy and time can be entangled. Has been observed in quantum dots. Polarization. Polarization is spin, isn't it? Polarization states of photons or other particles. For instance, entangled photons with orthogonal polarizations have been generated and used for quantum communication. I thought you can't use it. Okay.
The only one. Just kidding. So if you had an electron in a box, quantum theory says it can be both spin up and spin down at the same time. Schrödinger thought superposition was weird because it's unintuitive for something to be two different things at the same time. It'd be like a cat in a closed box being both dead and alive at the same time. But when you open the box and observe the cat, it instantly is just one state. It's dead. Or it's alive. And this is real life stuff. And it gets weirder. With quantum entanglement. Imagine two kittens, each in a box, who happen to behave like quantum particles. Their two possible states are asleep and awake. Each kitten has a 50% probability of being awake and 50% probability it's asleep. They're in that weird state of both. And they're not just any quantum kittens, they are entangled, which basically means that their fates are connected. Determine the state of one and you will instantly determine the state of the other. Mess with one and you will affect the other one instantaneously. So for example, you could have two entangled kittens wherein one has to have the opposite state of the other. So both kittens start in a superposition of awake and asleep. You open one box, observe kitten, find it asleep, so the other one must be awake. You could separate these kittens to opposite sides of the planet and you'd still get the same results instantaneously. Do you see why this is weird? It's almost like the kittens or quantum particles communicated with each other
I don't see why it's weird. I see what you're telling me is weird. I don't see why quantum entanglement is real. You're not showing anything. You're telling me a story. The story is weird. Yeah.
and you'd still get the same results instantaneously. Do you see why this is weird? It's almost like the kittens or quantum particles communicated with each other instantaneously and telepathically. This was enough to freak Einstein out. You may have even heard of his overquoted description of it. Spooky.
No, this is a complete misunderstanding. He was never. What did you say?
Particles communicated with each other instantaneously and telepathically. This was enough to freak Einstein out. You may have even
That's good. That's what I say.
heard of his overquoted description of it. Spooky action at a distance. Quantum mechanics says that entanglement is real. This was enough to freak Einstein out. You may have even
It did not freak Einstein out. What are you talking about?
heard of his overquoted description of it. Spooky action at a distance.
No, he never said. He refused to accept. He said that's telepathy. He said it's telepathy, which is obviously nonsense. We know there's no telepathy. Where's telepathy? If this is possible, then evolution would have used it. If it would have been useful, evolution would have used it. We would have developed telepathy. Telepathy is very useful. We don't use telepathy. So that's it. Why don't we see it on the macro scale? This nonsense. Literal nonsense.
Quantum mechanics says that entanglement is real, even if it's weird, and we've seen its effects in many, many experiments. But there's still a slim chance it's just an illusion. Like this trick. It's funny because for a split second, the kid actually thinks their head is full of coins. So when it comes to entanglement, maybe the physicists are the kids who haven't figured out yet that the hand brought the coin there. Like maybe it just looks like entangled particles can communicate instantaneously, but it's just some trick of the universe pulling it off. Dave Kaiser is checking for a mystery hand creating the illusion of entanglement. He's looking for some unknown thing, and he knows it's a little far-fetched.
So it turns out, think there's a lot of good reasons to still believe and have great confidence in quantum mechanics, and I had that assumption going in.
You may as well be looking for a unicorn.
So it turns out, think there's a lot of good reasons to still believe and have great confidence in quantum mechanics, and I had that assumption going in.
You may as well be looking for a unicorn. He's pretty sure unicorns don't exist, but he hasn't logically disproven it yet, which for physicists means that it's possible. Unlikely, but possible. So Dave and his experimentalist colleagues came up with an idea for an experiment to test for this invisible hand fooling us.
And so we were able to put the team together. So by 2015, or so we had things in place.
So how do you look for something when you don't know what you're looking for? You do what YouTube is doing to you right now. You collect statistics in a clever way conceived by physicist John Stuart Bell.
Just over 50 years ago, in 1964, John Bell, a really great, very creative physicist, published an article that was really not very much noticed or talked about in his day, but it has come to be this really incredibly interesting thing. And his argument was that one could actually put to the test, put a real experimental quantitative test, a debate that had already been raging for 30 years before that.
Bell figured out that if measurements on close kitten were independent of faraway kitten, then the results of tests on the pairs of kittens could only line up so often. They'd obey an upper limit known as Bell's inequality. But if the kittens were genuinely entangled, then measurements on the pairs of kittens should line up more often than Bell's.
No one is arguing that they are really entangled. They are really entangled. Okay, but there's nothing special. There's nothing spooky. They are created with a hidden variable that entangles them.
Limit would allow. Quantum theory predicts their behavior should be more strongly correlated with each other. People have taken
What does that mean? Why does everybody keep saying that, but no one actually explains that?
lots of statistics on entangled photons, and everything so far supports that entanglement is real. But physicists argue that there's a slim yet real possibility that these experiments are flawed. In come Dave and his colleagues. They sent pairs of entangled photons in two directions.
So we set up in the city of Vienna, and we shot lasers to the night sky of Vienna. First of all, let's just pause on that for a second.
That's amazing.
It's amazing. So we set up a very powerful laser in Anton
He's gay. They're all gay.
laboratory near the roof, and that shot these entangled particles, really specially prepared laser light, half a mile.
Why are they all gay? What are you get?
in this direction, a mile in that direction.
One got sent to a telescope at a university and the other to another detector at the Austrian National Bank. These detectors were designed to make a measurement, like checking whether the kitten is awake or asleep, but in this case determining the polarization state of the photon. The thing is, the measurement depends on how the detector is oriented, and you have to set that before your measurement, which is the crux of the experimental test here. In the past, people have worried that somehow something could have biased the detector settings. Either one detector was transmitting information to the other, or the person operating was somehow unconsciously biased, or who knows why. But Dave and his team came up with this crazy idea to make sure that their detectors were not biased. Because human influence things are notoriously bad at generating random numbers. So instead of using conventional random number generators to set the detectors, they decided to use giant burning balls of plasma. Yeah, stars. Each detector had an accompanying telescope pointing at a different star in our galaxy, closest of which was 600 light years away. And as each photon from the star hit the telescope, the detector would reorient itself depending on the random color of the starlight. So cool. They were using starlight as a tool in their experiment. The detectors were randomly resetting after the entangled particles were emitted, but before they arrived at the detectors. So the measurements performed on each particle couldn't have been known at the time the particles were created. They counted them up and looked for correlations between the measurements, and they found them. They found exactly what quantum mechanics said that they would find. So in the end, the only way that entanglement could have been fake is if something had interfered over 600 years ago to bias the detectors.
What? What are you talking? Why do they keep saying that nonsense? I don't get it.
Because 600 light years, as I said, that's before there was a Gutenberg printing press. What I'm fond of saying is when Joan of Arc was so young, her friends still called her Joni. And that's still a long time ago.
Yeah, like the Knights of the Crusades, or the Mayans. And they would have had to have been at that star 600 light years away. Anyway, it seems pretty convincing that entanglement is real, but Dave thinks he's just narrowed the odds of finding his unicorn. He eventually wants to use the oldest light in the universe, maybe even cosmic microwave background to set his detector. That way we can make sure that no bias snuck into the experiment since the Big Bang.
What is this nonsense?
So part of this is just that, like, quantum mechanics came along and it was weird and it made people uncomfortable.
Yep.
And this is like, let's make sure we're validating it. Let's make sure that it is true through all these different experimental means, and checking any ways that there could be some weirdness sneaking into the experiments.
That's right. I don't know anyone in the field who says, I think this is a plausible alternative to quantum mechanics. And I don't. I don't think this is like really how I think the world's going to work if we can zoom in and watch it unfold. But there's still some, I think, interesting motivations to keep trying. People around the world, as you know, are working hard to build actual industries now, at the basis of which are things like quantum entanglement. The whole spheres of quantum.
What a waste of money. Trillions are going to go down the drain.
Of computing, of quantum encryption, of quantum teleportation, everything else people dreamed up for Star Trek many years ago. All these ideas depend at their core on quantum entanglement being real in the world, not just some trick that somehow we got duped by in a handful of experiments.
So no cracks in the foundation of quantum mechanics, which is great because that means I can still use it to explain how lasers work. But not now. I have some hats to play with. But thank you for watching this video, and happy physics.
How lasers work? Nothing to do with that.
Thanks to 23andMe for sponsoring this episode. The name 23andMe comes from the fact that human DNA is organized into 23 pairs of chromosomes. 23andMe is a personal genetic analysis company created to...
I don't understand. I don't understand the test.
And his argument was that one could actually put to the real experimental quantitative test, a debate that had already been raging for 30 years before that.
Bell figured out that if measurements on close
What is the debate?
kittens were independent of faraway kittens, then the results of tests on the pairs of kittens could only line up so often. They'd obey an upper limit known as Bell's inequality. But if the kittens
What is this upper limit that they keep talking about?
were genuinely entangled, then measurements on pairs of kittens should line up more often than Bell's limit would allow. Quantum theory predicts their behavior to be more strongly correlated with each other. People have taken
I can give you 100% correlation. There's no more than 100%. I can do it, and I've done it.
lots of statistics on entangled photons, and everything so far supports that entanglement is real. But physicists argue that there's a slim yet real possibility that these experiments are flawed. In come Dave and his colleagues. They sent pairs of entangled photons in two directions.
So we set up in the city of Vienna, and we shot lasers to the night sky of Vienna. First of all, let's just pause on that for a second.
This is amazing.
Oh. $6:30. I don't want to even make a comment. You can't speak against these people. They are the elites. Oh my God. War, Kennedy. I think this is the library where he works. This can't be his personal books. Fermi, illustrious immigrants. We know now. Critical masses. Bengali. Harlem. Empire of reason. Difficult to tell. The Republic of Mass Culture. The culture of the Cold War. Masters of Deceit. The Big Test. There's no physics here, so no, this is not a library. A library would not have this. This is his office, home. Energy. Freeman Dyson. atomic power, clear muse, Herman Kahn, power, using nature.
It's amazing. So we set up a very powerful laser in Anton's laboratory near the roof, and that shot these entangled particles, really specially prepared laser light, half a mile in this direction, a mile in that direction.
One got sent to a telescope at a university, and the other to.
He's not explaining the experiment. Like, it looks like it's two different laser beams, but it's not. It's one laser beam, and they split it into two laser beams, into two laser beams, something like that.
To another detector at the Austrian National Bank. These detectors were designed to make a measurement, like checking whether the kitten is awake or asleep, but in this case determining the polarization state of the photon. The thing is, the measurement depends on how the detector is oriented, and you have to set that before your measurement, which is the crux of the experimental test here. In the past, people have worried that somehow something could have biased the detector settings. Either one detector was transmitting information to the other, or the person operating was somehow unconsciously biased, or who knows why. But Dave and his team came up with this crazy idea to make sure that their detectors were not biased. Because human influence things are notoriously bad at generating random numbers. So instead of using conventional random number generators to set the detectors, they decided to use giant burning balls of plasma. Yeah, stars. Each detector had an accompanying telescope pointing at a different star in our galaxy, closest of which was 600 light years away. And as each photon from the star hit the telescope,
Why is that relevant? Why is the source of the light relevant?
detector would reorient itself depending on the random color of the starlight. So cool. They were using starlight as a tool in their experiment. The detectors were randomly.
But how are they entangling the two photons? I don't get it. So this is this is not. Oh, they use the starlight to orient, to create the randomness. Okay, so the randomness is the orientation of the star. Okay, some randomness. Okay. What? Oh, hey, Tapioca Weasel. They have a romantic entanglement. That's how? uh, Hey, what's up? Glad you're watching. Oh, there you are. Let's see. Okay, let me see. Trillions. You overestimate our funding. Wait, I said I don't remember saying trillions this today. Boo, you aren't watching the. No, it's impossible to watch it. There's no way to watch it. I wish I could. Make a comment if you want to make a comment. That could be his library, but it might not be. I meant office. I think it's his office. It's not. I doubt it's his library. Anyway,
Quantum mechanics.
I wish I could talk to you about this because I just don't understand what is surprising. Like I wrote papers, but I also wrote programs. Where's my programs? Collab. So I showed you one of them. Sorry for blinding you. So this is the one, I think I showed it already. Maybe I didn't show it to you, but this is the other one. This is the more important one. So this is so I actually added a hidden variable. This is I'm 100% correlated. I can reproduce any experiment without telepathy. So this is right. This is up down. It's always up down or down up because they're 0 degrees apart in the measurement, but they are 180 degrees apart in the creation. And anyway, so I'm creating two particles, right? Two random spin. I'm creating a random spin, and the opposite is entangled by 180 degrees. And then I'm creating a randomness variable on top of two random spins, or two opposite but random spins. Then I'm creating particle 1 and particle 2 with each with opposite spin, but a shared random value. This is the flip of the coin. So upon creation, they share the randomness that they will use in order to randomize the detection, the measurement. And then I say particle 1, particle 2 measure, and I give them the measurement angle, and I can obviously randomize it as much as I want. And here is the, right upon creation, I save the spin angle and the randomness. And then when I tell a particle to measure itself, I give it the angle. And then I calculate the delta angle between the measurement and the spin. This is each particle now. So particle A, for example, or particle B. So this is the difference. This is the effective moment, I guess. So the difference between my spin as a particle and the measurement of the magnetic field. And this is a correction for if it's over 180, whatever. I don't know exactly what's this. Anyway, and then this is the angle over 2, the delta angle that we just calculated, delta over 2, cosine squared. I'm allowed to do any calculation I want as long as I'm not doing telepathy, right? I'm just trying to disprove telepathy. So I can use cosine squared. Who cares? I can do whatever, right? This has to do with the actual mechanics. There's no telepathy here. So you can't tell me not to use this. This is completely meaningless. And then I take okay, so that's, let me think. Okay, so this is the cosine squared. And then I want to calculate how influential is the randomness. So I have with me, right, every particle has, upon creation, received a flip of a coin, the randomness. But I want the randomness to be relative to the sine squared of the delta angle. I want to increase. I want to increase and decrease the amount of randomness, right? Because when they are when the apparatus of both measurement is pointing in the same direction, I want zero randomness. Right? This is allowed. I can do anything I want as long as I'm not sharing information. There's no telepathy, so I'm allowed to do anything I want. I'm just manipulating the randomness. So that's the randomness influence. And now let's see whether it's up or down. So that's the base probability. That's just the cosine squared. But then I'm correcting it relative to the randomness influence. And that's the answer, up or down. And it's as correlated as you want. There's no stronger correlate. You cannot tell me that there is, right? You cannot tell me about Bell's inequality, that I'm limited by the correlation. I have no limit to my correlation. The two particles are exactly 100% correlated because their spins are correlated and the measurement, and the randomness is correlated. The randomness is the same, and the spin is 180 degrees off, or if you want, you can have them both pointing in the same direction. And that's it. And I can reproduce any experiment that you want. I don't understand what they're even talking about. I'm able to reproduce any experiment you want. 0 degrees, 90 degrees. This is going to take a while because it has to load the thing. Oh, you wrote more comments. I too think it is his office. All right. Did you write? No, I told ChatGPT to write it. I wrote the instructions for ChatGPT. How does cosine squared come from? I don't care. As long as there's no telepathy, right? We're just trying to disprove spooky action at a distance. I can do any calculation I want, right? We're just trying to eliminate spooky action at a distance, telepathy. I'm not disputing it, but since you brought it up, I'm curious. Oh, I think ChatGPT. This is ChatGPT code. This is his code, not mine. So I gave ChatGPT the instructions, and there's a paper that explains it, and I have the prompt. You can play with the prompt. So that's it. So here we ran it, and that's it. You have 50-50 because it's 90 degrees. It's perfect, right? So when particle 1 is up, then particle 2 is also up, but some of the times particle 2 is down when particle 1 is up, and vice versa. This is completely random. And if you go for 45 degrees, I mean, it doesn't matter. I mean, I can play with whatever results you want to get. Tell me the results you want to get. I'll produce the results for you. I have 100% entanglement without spooky action at a distance. This is 45 degrees, which means they're closer to being aligned. So since I mean the right the spins are opposites, so you expect more up down than up up. There you go. But you tell me whatever ratios you want to reproduce, I'll reproduce for you. It's silly. I'll play, I'll tell ChatGPT, you tell me whatever you want to reproduce, I'll reproduce. I have exactly 100% strength of correlation. Like people say, the correlation is not as strong when you have hidden variables relative to quantum mechanics. That's false. The correlation is exactly 100%, and there is nothing stronger than exactly 100%. So I don't understand what they're talking about when they say it's the right. Bell's inequality is that there is an inequality of strength of correlation between hidden variables and telepathy. But I don't. No, there isn't. No, that's incorrect. That's like absolutely incorrect. This is I can give you 100% correlation. Then there's nothing stronger. So Bell's inequality is incorrect. So if you're relying on Bell to prove some inequality, then that's wrong. And I don't know what I don't understand what experiments these people are doing, because I mean, whatever experiment, it doesn't even, I don't care what experiment they're doing. Whatever the experiment they're doing, tell me the data and I'll reproduce it, because I have 100% correlation. I can play with it however I want. I'll add here whatever you want. I can play with it however I want, and then with hindsight we'll explain the mechanics. I don't care. We're just trying to disprove the telepathy part. Well, don't you want some mechanical argument for the math? No, I don't care. I don't care, because we're trying to disprove telepathy. I don't want to talk right now about anything else but telepathy. I don't want to confuse the debate. I don't care what the mechanics is. It doesn't matter. It doesn't. That's not the point. Fine, then we don't understand the exact forces, schmorses. I don't care at this point. This is infinitely more important. The telepathy. I'm disproving the telepathy, and I'm done. I don't know what else to do. Like, I don't know who to talk to. There's no one to talk to except for you. And I'm spinning in circles because I don't know what else to do. I'm trying. I don't know how much more. What more do I need to prove or disprove the telepathy? What else do I need to do? I mean, I didn't need to do this. I did not need to do it. I didn't need to do it because because it's obvious. So I don't even understand what these people, I don't even understand what they're talking about. But now that I've done it, what do you want now? So I can argue from reason, okay, but here it is. But I mean, it makes perfect sense that there's nothing strange. There's nothing spooky. Anyway, I don't know what to say. I wish I knew who to. Besides you, I mean, do you want to write a paper together? You can be the lead writer. I'll just be the you can. I don't care if you give me credit. I'm just tired of entanglement. I don't want to hear that word ever again in my life. Because I'm not here for the entanglement. I'm here for ether. Actually, I'm neither. Um, so tell me if you want to write the paper together. I mean, I can. Let me see. You need to prove you understand the theory because it's not telepathy. That's what you need to prove for me to take you seriously. I don't know what you mean. I don't know what you mean. Explain. And you aren't even close. I'm sorry. Close to what? Close to what? Explain. I don't know. What do you want me to prove? Tell me what you want me to prove. You need to tell me what you want me to prove. Like, I can prove anything because I have 100% entanglement without telepathy. I've entangled the two particles with a hidden variable. What else do you want me to do? You need to prove you understand the theory. What do you mean? What theory? There's no theory. I know. I need you to demonstrate that you can articulate our theories in a way that we agree. Tell me what you want me to do. I'll do it. Besides, besides that, but tell me what you what. Ask me a question. I don't know what it means. I need you to demonstrate that you can. I told ChatGPT here. Let me show you the instructions I gave ChatGPT because that ready paper, software simulation. I think this is it. Yeah, this is it. Here's the prompt. Please write a Python script. Generate a random value, create two particles with random opposite spins and this random value. Each spin will be a number between 0 and 360 degrees inclusive. Call on both particles measure with measurement angle, where measurement angle is 0 degrees. Measurement angle needs to return up or down. Up or down will depend on the difference between the particle's spin direction and the measurement angle, but also on the particle's random value. The random value should be weighted more lightly as the above difference is smaller. Maximum randomness at 90 degrees, and again smaller randomness as we get closer to 180 degrees, with the randomness 0, a difference 0 and 180 degrees. Notice that measure should not call NP random rand. Rather, measure should use the random value that was passed to the particle at creation. Run this test 1,000 times, plot the results, columns up, up, down, down, up, down, down, up. Show the actual numbers for each column. And this is the explanation. This is ChatGPT's explanation. If you want to ask ChatGPT why measure looks like that, probability calculation, the probability measure up depends on cosine squared of half the angle difference, which is common in entanglement experiments. We add whatever the reason they give for cosine squared. I'll take it for now. I don't know what the reason is. I mean, we add a randomness influence that varies with the angle difference peaking at 90 using NP sine, NP radians, delta angle squared. The randomness value modulates the influence, which is highest at 90 and 0 at 0 and 180. The final probability of getting up is a weighted combination of the intrinsic probability and the randomness factor. That's it. I mean, well, what else do you want me to do? Tell me what else you want me to do. That's what I want. I want you to understand the models you are disputing. The reason is literally the thing you are disputing. there's no telepathy. I'm able to reproduce 100% entanglement without telepathy. That's it. There's nothing else. When they say Bell's inequality is the inequality of the strength of the correlation between um, a hidden variable and telepathy. That's the inequality. So I say that's incorrect. Bell's inequality is incorrect. It's equal. That's it. And here is the proof. It's equal. There's no inequality. Bell's inequality is incorrect. There's no inequality. Well, I don't know what else to say. Why would you say that their entanglement is less strong through a hidden variable? Here is the hidden variable. This is the most important, in this case, hidden variable, this randomness. This is the hidden variable. So why would that be less strong than telepathy? This reproduces telepathy. This is the telepathy, right? Because you're saying that in real time, right? The claim is, Bell's claim is that in real time, they can't be flipping a coin in real time because they must be flipping the same coin in real time to get the measurement, a correlated measurement. So all I did is I just said no. They can flip a shared coin at creation and carry the shared coin flip result during their lifetimes until we measure them. So the measurement is correlated. It's really very straightforward. I don't see, and that's a hidden variable, and we're done. I don't need telepathy. Why do I need telepathy? If I can explain this, if I can explain 100% strength correlation, I can explain it with a shared hidden variable. This is the shared hidden variables. I can explain 100% strength of entanglement using a simple hidden variable upon creation. So why do I need to share a variable in real time and violate the laws of nature if I can share the value upon creation and not violate the laws of nature? I mean, they're claiming that there is a flip of a coin in real time, and all I'm saying is, why do you don't need to say that. The flip of the coin is done upon creation. When the two entangled particles are created and become entangled, at that time the flip of the coin is already done then. There's no more randomness. I told ChatGPT explicitly, don't randomize measure. Measure should not call any randomness, should not be randomized. So I made a notice that measure should not call NP random rand. Rather, measure should use the random value that was passed to the particle at creation. That's the trick. The trick is to force ChatGPT to write code that doesn't randomize measure. So you randomize whatever you want to randomize, you randomize during creation. Anyway, tell me what you want, because as far as I'm concerned, I'm done. I don't know what else to do. I'm like, I'm chasing my tail at this point. I'm watching anyone's video, trying to understand what. Maybe I misunderstood something. Maybe I don't know. I mean, I'm watching anyone and everyone's explanation of Bell's theorem, and everyone basically says the same thing, and to me it's nonsense. So I don't know what to do. So I wish you would tell me what data, right? You need to tell me what data you want me to reproduce, right? At the end of the day, if I understand entanglement correctly, the way to disprove entanglement is you want me to reproduce the data without telepathy. Well, I've done that. I've reproduced the data without telepathy. I don't know what else to do. You tell me what else to do. Right? The whole word Bell's inequality. The inequality is the inequality of strength. I don't see an inequality of strength. Why would there be an inequality of strength? Where would the inequality come from? I don't understand where the inequality comes from. Whatever, right? Because you claim, oh, it's telepathy. Okay, why does the telepathy have to happen when they're far apart? Why could it not have happened upon creation? And then you don't need telepathy. And then you have 100, whatever. Oh, you're writing an answer. Let me see. Oh, let me see. 1 second. Oh my God. I want you to reproduce the work that physicists did to understand physics, the math, the classes, the practice. I don't know what that means. You need to show me the data. Show me the data that you want me to reproduce. I don't know what it means, the work that physicists did to understand. I don't know what that means. I don't know what that means. The math, the classes, the practice, that's what I don't understand. Please, I don't know what that means. I need, like, I don't know what that means. It's like the meme. What do you mean? What do you mean? What do you mean? What do you mean? I don't know what you mean. I don't know what you mean. I wish I knew what you mean. Well, what do you want me to reproduce? You need to put in the work. There is, but at this point, there is like hundreds of hours of me. Uh, you haven't? And you don't even know what I mean. Yeah, I don't know what you mean. I mean, I wish I knew what you mean. I don't know what you mean. And I've put in as much work as possible. You see, I am. That's all I'm doing. I'm doing just quantum entanglement at this point. I haven't done any ether work. I mean, I started writing a new paper about the ether. Really interesting. That Mond. Where's the paper? What's going on? Let me refresh this page. So they discovered that Mond. I was watching Sean Carroll, a solo episode by Sean Carroll about the crisis in physics, and he brought up this unbelievable fact that Mond, modified Newtonian dynamics, has been disproved. So Mond violates the inverse square law, hence invalidates gravitational ether, because the ether depends on, right? The ether produces the inverse square law. But Mond having been ruled, right? Mond has been ruled out due to damping of even numbered peaks in the CMB. I didn't, he explained it. I started following what he said. Anyway, really interesting. But I'm barely touching it. I want to write this paper, but all I'm doing right now is ether. Is not ether. I'm just doing entang. I didn't mean to. Anyway, you need to tell me what you want me to do. Like what proof? What do you want me to prove? I proved. I don't even think I need to prove anything. I mean, Bell's inequality claims that there is an inequality between telepathy and non-telepathy. And I don't see how, why do you need that, right? Because whatever telepathy you have in real time, right? Each particle in real time decides how to be measured, right? That's that. Let's say each particle but they decide together in real time, randomly, how to be measured. Fine. Why do you need this decision to be in real time? Why can't this decision be upon creation? And then you don't need telepathy. That's all. I'm just asking, as the as people say. I'm just asking questions. I'm just asking, why do you need telepathy? Why do you need spooky action in a distance if you can get the same result of a shared decision, a shared measurement, right? You want to correlate the measurement. Okay, so you're saying, oh, they're conspiring in real time while violating the speed of light. Okay, fine. That's one option. Another option is that the communication, the telepathy, right? Whatever information is there in the telepathy, about, right? It's all about the measurement. That discussion, that telepathic discussion, what if it took place upon creation? They decided, they conspired not during the test. They conspired during their creation to to come up with the same measurement. Um, you have to go to sleep. Talk to. Oh, oh, I have. All right, man. Thank you. I appreciate. I really appreciate your time. You're the best there is. I wish everybody was like you. Anyway, yeah. Okay, that was good. That was a good discussion. Tapioca Weasel is the best person in the world, as far as I'm concerned. Um. All right. What else? What else we got? I mean, I don't know. I mean, this is a surprising experiment. This I need to still go back to and understand. But no one, besides them, no one has this experiment. They're the only ones to have this experiment. It is their experiment is really weird. I don't know. But everyone else's experiment is really straightforward and can easily be explained with a shared hidden random variable. Anyway, you know what? We've been here for 46 minutes, but a lot of it has been just this discussion. So I'm going to run to the bathroom. Let me stop. Let me change the name to oh, uh, discussion with Tapioca Weasel about quantum entanglement, bells in Since when do we get so much autocomplete in Windows? This is a new thing for Windows. They just added this today or lately. Discussion with Tapioca Weasel, quantum entanglement, Bell's inequality. What else we got? Hidden variables, hidden variables. I guess telepathy. Oh, that's the end of that. All right, 100%. Save changes. All right. Let me go. I'll be right back. Bye bye for now.